Hello, hello. All right, I think we're recording. We are going to start on slide 15 of the chapter 16 PowerPoint. We're going to learn how to mathematically manipulate equilibrium constant expressions. So we'll start with this simple equation: solid carbon plus oxygen gas reacts reversibly to form carbon dioxide gas. And if we were to write the equilibrium constant expression for this, we'd note that the equilibrium constant would be the concentration of CO2 divided by the concentration of O2, and we wouldn't include carbon in there because carbon's a solid. Let's see what happens if we double this chemical equation. If I do that, I'm going to get twice carbon plus twice oxygen reacts reversibly to form twice carbon dioxide. Now, if we were to write the equilibrium constant expression for this equation, we'd get the following. Let's call this one K1. We'll call this one K2. So here we'd have carbon dioxide squared divided by the concentration of O2 squared. And notice that if we take K1 and multiply it by itself, well, we'd get concentration of CO2 divided by the concentration of O2. That's this. We'll do it one more time. And hey, look, this numerator, that's just CO2 squared, and the denominator is just O2 squared. So that's identical to the equilibrium constant for the doubled equation. So notice what's going on here. If we multiply an equation by a stoichiometric factor, in order to find the equilibrium constant for the new reaction, we take the old equilibrium constant and take it to the power of the stoichiometric factor that we multiplied the original equation by. Whew, that's a lot of words there. So let's look at this one more time. This equation has this equilibrium constant. I doubled this equation to get this one. And what happens if we want the equilibrium constant for this second equation, what we can do is we'll take the first equilibrium constant ratio and we'll just raise it to the power of however much we multiplied the original equation by. In this case, we multiplied it by 2, so we square it. If we were going to multiply this, say, by 3, well then K3 for this expression would be equal to K1 cubed. Okay, let's move on to slide 16. Let's start with our original equation again. Solid carbon plus oxygen gas reacts reversibly to form CO2 gas, and we know that our equilibrium constant for this particular reaction is the concentration of CO2 divided by the concentration of O2. In this case, we're going to reverse the original equation. So that means the product's going to become reactant, and the reactants are going to become products. So I'm going to go CO2 gas reacts reversibly to form solid carbon and O2 gas. Let's see what this new equilibrium constant is. We'll call this one K1, and we'll call this one, well, I don't know what we're going to call this one. We'll call it K prime, all right? So that's going to be equal to the concentration of O2 divided by the concentration of CO2, products over reactants. I don't include this because there's a solid. Look at the relationship here. If I reverse the equation, as I did here, to get the new equilibrium constant, I take my original ratio and I just flip it. See, I just took the inverse of it. Here, O2 went to the numerator, and here, CO2, which was originally on the numerator, went to the denominator. So therefore, if the equilibrium constant for the reverse reaction is just the inverse, you flip the fraction, it's just the inverse of the equilibrium constant for the forward reaction.